Okay, let's get started. Today we're going to continue our discussion on rasterization. Last class, we took a look at some of the techniques that we can use to rasterize different primitive shapes like lines and triangles. For rasterizing triangles, we took a look at these half-plane tests, where for each edge of the triangle, we construct a half-plane that passes through that edge. And given a point P, we are going to test if that point is inside the half-plane or outside the half-plane. And we repeat this half-plane test for every single edge of the triangle. If the point P is inside all three half-planes formed by the edges of the triangle, then this is an indication that the point is inside the triangle. If the point is outside of any one of the half-planes, then this is an indication that the point is outside the triangle. To perform these tests, we went over how we can construct the implicit line equation for a particular edge, and then use that line equation to test if the point is inside or outside the half-plane. So if a point is inside all three half-planes, then we can safely say that the point is inside the triangle, and we can color in that point accordingly. But if the point is outside any one of the half-planes, then it's outside the triangle, and we don't have to color that particular pixel. Okay. Now, if the point is inside or outside the triangle, then these are relatively easy cases to handle. But next, let's take a look at some trickier edge cases, where the point lies exactly on one of the edges of a triangle. So let's say our pixel P lies exactly on one of the edges of the triangle. And we now have to determine how we handle these edge cases. When we are rasterizing complex meshes with thousands of triangles, we have to be careful in terms of how we handle these edge cases to make sure that it doesn't lead to any artifacts when rendering those more complex shapes. So let's take a look at some different ways that we can handle these edge cases and what some of the trade-offs may be. So first, maybe a simple strategy that we might come up with would be, we can say that all pixels that lie on the edge of a triangle will be considered outside of the triangle. So in that case, we won't color in any of the pixels that lie exactly on an edge. So let's take a look at what happens with this particular convention. Suppose we have a very simple mesh that consists of a green triangle and a blue triangle. And we now want to rasterize these triangles onto a grid of pixels. Now, let's say that the edge that's shared by these two triangles the pixels along this edge lie exactly on the edge of this triangle. So this means that the center of the pixels are exactly on this edge. So now let's see what happens when we rasterize these two triangles. So first, we are going to rasterize the green triangle, and this will color in these particular pixels. Now, because these pixels lie exactly on the edge of the triangle, and we say that pixels on the edge of a triangle are considered outside of the triangle, then the pixels that are along this vertical edge will not be colored in. So we're going to leave those blank. Next, we're going to color in the blue triangle, and we'll end up coloring in these particular pixels here. And again, the pixels that lie exactly on the edge won't be colored in because they're considered to be outside of the triangle. And this then leads us to some undesirable artifacts. Geometrically, these two triangles share an edge, which means that there should not be a gap between these two triangles. The edge should be completely filled in. But because we said that any pixel that lie exactly on the edge would be considered outside of the triangle, we end up running into this edge case where the pixels that are shared between the two triangles are actually not colored in. And this then leads to a bunch of gaps in our mesh. So if we have a more complex mesh that has a larger number of triangles, and we use this particular heuristic, then instead of seeing a continuous surface, we're going to see a bunch of gaps everywhere in our mesh. And this is not really a desirable result. Okay, so unfortunately, this simple idea doesn't quite work. Okay, so if we don't want any gaps between triangles, then maybe an alternative strategy would be we can say that all pixels that are on the edge of a triangle will be considered inside a triangle. All right, so let's take a look at what happens with this particular heuristic. Again, we have these two triangles, and we are going to focus on the edge, on the pixels that lie along the vertical edge that's shared by these two triangles. First, we are going to color in the green triangle. So that's going to color in these particular pixels here. Unlike the previous convention, the pixels that lie along the edge of this triangle are colored in. So that seems good. Doesn't seem like that we're going to get any gaps along that edge. Next, we are going to color in the blue triangle. And then we're going to end up coloring in the pixels, these pixels here. And when we color in the blue triangle, we end up seeing some maybe slightly undesirable effects. And that is that the pixels that are along the vertical edge are now replaced with the color from the blue triangle. So when we color, in the green triangle, we colored in all of those pixels along the edge with a green color. But when we rasterize the blue triangle afterwards, we end up replacing all of those colors along the vertical pixels with blue instead. So we end up drawing into the same pixels twice. So this might not seem so bad, but it can actually lead to a very undesirable artifact. Okay, so to see these artifacts, let's say we render the triangles in a different order. Instead of drawing the green triangles first and then the blue triangle, let's say we rasterize the blue triangles first. So we're going to rasterize the blue triangles first, and we're going to color in these particular pixels. The pixels along the vertical edge will now be colored blue. Next, we are going to color in the green triangle, and then we are going to replace all of the colors along the vertical edge with green. So now the pixels along the vertical edge will now be colored in green instead of blue, like in the previous example. What this means is that the resulting image that we get by rasterizing these different triangles now depend on the order in which we draw the triangles. So depending on which triangles get drawn first, we can end up getting a different image at the end. And this can lead to some undesirable artifacts where, let's say, the colors along the edges of that shared by triangles might flicker between different colors, depending on just the ordering that we draw those triangles. So unfortunately, this particular strategy is able to ensure that we don't get any gaps between triangles, but kind of introduces an order dependency on the order in which we draw the triangles. So this is also undesirable. Ideally, we want to get the same image back, regardless of what order we draw those triangles in. So unfortunately, this second strategy also doesn't quite work. Now, before we take a look at a heuristic that we can adopt that can fix some of these edge cases, any questions about any of this before we move on? So fairly clear why these simple strategies don't work. Yeah. So in order to correctly handle these edge cases, we need to adopt some consistent conventions that would avoid these different artifacts that we just saw. So in general, there are no correct way of handling these edge cases. The key is that we just have to find some consistent conventions that we can stick to and apply those conventions to consistently across all of the triangles that we draw, so as to ensure that we get consistent results. So in practice, a very common heuristic that's used to handle these edge cases when drawing triangles is what's referred to as the top left rule. The idea with this top left rule is that we are going to color in pixels that lie on the edges of the triangles if they belong to one of two possible cases. We are going to color in a pixel if that pixel lies either on a top edge or a left edge, which is why this is called a top left rule. So on the right here, we have some example of these very tricky corner cases, where edge and corner cases when rasterizing triangles. And this is an illustration of the heuristics, the conventions that are adopted by most rasterization pipelines in order to handle these tricky cases. So let's go into the details of how this top edge rule works. So we're only going to color in a pixel if it lies on either top edge or left edge. But let's take a look at how we define these two different types of edges. So a top edge will be referred to as an edge that lies, is a horizontal edge that lies at the, it's a horizontal edge that lies at the top of a triangle. So for this particular edge that's shared by a dark gray triangle and a light gray triangle, this particular edge will be the top edge for the light gray triangle on the bottom. And it's not going to be a top edge for the dark gray triangle on top because it's not the top edge of the triangle. Now, similarly, a left edge will be defined as an edge that roughly lies on the left side of a triangle. So for this particular edge here, that's shared by the light gray triangle and the dark gray triangle, this particular edge will be the left edge of the dark gray triangle on the right. And it's not going to be a left edge for the light gray triangle on the left. Now, a triangle can have multiple left edges. So this dark gray triangle has one left edge, but this light gray triangle actually has two left edges. So we're going to color in all of the pixels that lie on both of these left edges. So let's dig into the details of the definitions for these two types of edges a little bit more. We're going to define a top edge as an edge that connects the two highest vertices in a triangle. Okay, so a top edge has to be at the top of the triangle. Therefore, it has to connect the two highest edges of our triangle. And the second condition is that these two vertices have to have the exact same height. So for example, for this particular triangle, the two highest vertices are vertex 0 and vertex 1. And the edge, and these two particular vertices also have the same height. So in this case, the edge that's connecting vertex 0 to vertex 1 will be considered a top edge because it satisfies both of these conditions. It connects the two highest vertices, and the two highest vertices have the same y value, has the same height coordinates. So in this case, we can say that this is a top edge. Now, let's take a look at a different triangle. Let's say we rotate the triangle a little bit, and then vertex 0 and vertex 1, well, they still share the same height coordinates, so they satisfy the second condition. but vertex 0 and vertex 1 are no longer the two highest vertices of our triangle. So in this case, this is not a top edge. So hopefully that's fairly intuitive. This edge is not the highest edge in the triangle, so it's also not a top edge. Okay, but now let's take a look at a slightly trickier case. Let's say we take our first triangle and we rotate this triangle a little bit. The edge that's connecting vertex 0 to vertex 1 is still connecting the two highest vertices of the triangle. So this edge is still higher than any other edge in our triangle. So this satisfies the first condition. But now when we look at the second condition, it doesn't quite work out. The second condition says that in order for an edge to be a top edge, it has to connect the two highest vertices, and the vertices have to have the same height. In this particular triangle, V0 and V1 still have, V0 and V1 are still the highest vertices in our triangle, but the height coordinates are slightly different. V0 is a little bit higher than V1. So even though these are the two highest vertices of our triangle, because they don't have the same height value under the top left rule, we're going to say that this doesn't count as a top edge anymore. So when determining if an edge is a top edge or not, we really have to make sure that the two rules are both satisfied. Even if the two vertices are higher than any other vertex in the triangle, if the height values are not the same, we're still going to say that this edge does not count as a top edge. Okay, any questions about this? Okay. So the second condition that requires the vertices to have the same height can be a little bit unintuitive, but this is how the heuristic is defined. Next, let's take a look at our definition of a left edge. So first, to define a left edge, we are again going to assume that the vertices are ordered counterclockwise around the triangle. So again, we are going to follow the right-hand rule. The normal for the triangle is going to point out of the screen in this case. So if you use a right-hand rule, all of the edges are going to be ordered counterclockwise. Now, given this particular ordering of the vertices, we're going to say that an edge is a left edge if the endpoint is strictly lower than the starting point. So let's take a look at what this looks like. First, let's look at the edge that connects V1 to V2. V1 is higher than V2. So for this particular edge, the endpoint is lower than the starting point. And we can say that this is a left edge. So it checks out. Next, the edge that connects V2 to V0. Because the endpoint V0 is higher than V2, this doesn't satisfy the condition for left edge. So this is not a left edge. Next, let's look at the edge connecting V0 to V1. V0 and V1 have the exact same height. And the condition says that the endpoint has to be strictly lower than the starting point. In this case, because both vertices have the same height, they do not satisfy this condition. So this doesn't count as a left edge. Okay, next, let's look at a different triangle. In this case, the edge connecting V0 to V1 will be considered a left edge because the endpoint V1 is lower than V0. So this checks out. For the edge connecting V1 to V2, the endpoint V2 is again lower than V1, which means that this also counts as a left edge. So depending on the configuration of the triangle, a triangle can have one left edge or it can have two left edges. So unlike a top edge, where every triangle can have at most one top edge, for a left edge, a triangle can have multiple left edges. As a final example, let's take a look at this slightly rotated version of the triangle. The edge connecting V1 to V2, again, is a left edge because the endpoint V2 is lower than V1. But now, when we rotated the triangle a little bit, the edge connecting V0 to V1 is no longer left edge because the endpoint V1 is now a little bit higher than V0. Okay. So for an edge to be a left edge, it has to be, the endpoint has to be strictly lower than the starting point. A question in the chat about whether or not the y coordinate refers to the height in pixel space. Right, yeah, so the y coordinate refers to the height of the pixels once we have projected them onto the image plane. So it's not the y coordinate in row space, it's the y coordinate in pixel space, in image coordinates. Good. Any other questions about this? So this top left rule is the most common strategy that's adopted by most rasterization systems. And by adopting this heuristic, we can help to ensure that there are no gaps between adjacent triangles, as well as the rasterizer will give consistent results regardless of the ordering in which we draw the triangles. So by handling these edge cases consistently, we can draw the triangles in any way in any order we want, and we're still going to get the same final image. Now, one last little bit about triangle rasterization. And that is how we perform these inside and outside tests. So to check if a pixel is inside or outside of a triangle, we have to perform these half-plane tests for every single pixel. So a naive implementation of this triangle rasterization method will involve us testing every single pixel in our image against all three edges of the triangle. So this can be a bit expensive and very inefficient because chances are most of the pixels will be outside the triangle. Okay, so in practice, we'll often rasterize the triangles in a more efficient way. Instead of performing these inside-outside tests against all pixels in our image, we are only going to test for pixels that are contained within the bounding box of a triangle. So the bounding box is defined as the smallest box that fully contains all of the vertices in our triangle. And instead of testing all pixels in the image, we're only going to perform the inside and outside tests for pixels that lie inside this bounding box. Now, to construct this bounding box, we can do this very efficiently by just computing the minimum and maximum coordinates of the vertices of our triangle. So we can look at all three vertices of the triangle, and we can find the minimum x value and the maximum x value. And that will give us the x bounds of our bounding box. And similarly, we can get the minimum and maximum y values, and that will give us the y bounds of the bounding box. And then that will give you the bounding box that fully contains the triangle. So this can be computed very efficiently with just a little bit of code here. So this is just a little bit of optimization to reduce the number of pixels that we have to check when rasterizing the triangle. Okay, any questions about this? Fairly straightforward. Okay. Okay, so that's about it for rasterizing triangles. Once we have a way to rasterize triangles, we can pretty much draw any shape we want. Almost every object that we are going to draw in computer graphics will be represented by triangle mesh. So as long as we can rasterize triangles, we can pretty much show anything. Now, the next step in the rasterization process is how do we determine the color for a particular pixel? So let's say we have determined that a pixel is inside the triangle. So given this triangle, we have a pixel that lies inside the triangle. Once we have determined that the pixel is inside the triangle, the next step is to figure out what color we assign this pixel. Now, let's go back to how we define a mesh. We define a mesh by storing the coordinates of all the vertices in the mesh, so the x, y positions of the vertices. But as we mentioned before in the mesh lecture, in addition to positions of the vertices, we can also store some additional attributes at each vertex. One of those attributes can be a vertex color. So in addition to every vertex being specified a particular 3D coordinate, we can also specify different colors for every vertex. So now when we rasterize a triangle, every single vertex can have potentially a different color. So if I'm trying to color in a pixel in the middle of the triangle, then what color should I assign what color should I assign that point inside the triangle? So intuitively, let's say if one vertex was green, one vertex was blue, and one vertex was red, then intuitively we should expect that a point inside the triangle would be given by a color that's some combination of all the colors that's at the vertices of that triangle. So maybe intuitively we will expect the triangle to look something like this. So how do we get this kind of blending of the colors at the different vertices of a triangle? So a question about why is it not white, right? Okay, so the vertices are red, green, and blue. If we just color in the triangle as being white, then how do we color in the pixels at the corners of the triangle? Because when we said that, let's say vertex 0 is red, what we are saying that a point that's exactly on V0 is going to be given a red color. But if we assign other points white, then we are going to get this continuity where all the pixels inside the triangle will be white, except when we lie exactly at V0, in which the pixel will suddenly turn red. So that might not exactly be a very intuitive result. Okay, hopefully that answers your question. So kind of the intuition for like blending colors in a triangle is that the closer we are to one vertex, the more similar the color should be to that particular vertex. So the color of a point should be more similar to the vertex that it's closest to. So one way that we can get this kind of interpolation of colors inside a triangle is by using a method called barycentric interpolation. To see how barycentric interpolation works, it's helpful to look at a slightly simpler case. So let's take a look at how we interpolate colors on a line. So let's say we have this line that we've rasterized onto our grid of pixels. And we're going to define different colors on the vertices of this line. So let's say the starting point at V1 will be red, and then the end point at V2 will be blue. So when we rasterize this line, what we should expect is that the pixels at the two endpoints will adopt the colors of the corresponding vertices. So the pixel at the starting point should be red because the starting vertex is red, and then the pixel at the end point should be blue because the end vertex is blue. Now, as we color in the pixels in the middle of this line, what we should expect is that the pixels will slowly transition from red to blue as we get closer and closer to the endpoint. So as we move along this line, we should get an interpolation of the color between the two endpoints, depending on how close we are to the two different endpoints of the line. If we are closer to V1, then we should see a red color. And if we are closer to V2, we should see a more blue color. So when rasterizing a line, given a point in the middle of the line, we need to figure out what is the correct interpolation of the colors at the two endpoints for this point in the middle of our line. And one way that we can interpolate colors along a line is by using linear interpolation. With linear interpolation, we're going to determine the color of a point in the middle of the line, CP, as a linear combination of the colors at the two endpoints, C1 and C2. To interpolate between these two endpoints, we are going to define an interpolation variable T. And T is going to range between 0 and 1, depending on where we are located at the line. If T is 0, then we are at the starting point of the line. And if T is 1, then we are going to be at the end point of the line. So now if we are at the start of the line, T is going to be very small. So 1 minus T is going to be a large value close to 1. So we are going to give a high weight to the color of the starting point C1. And then C2 will be weighted by T, which is going to be a small value. Now, similarly, as we move closer and closer to the end point, the value of T is going to increase. So 1 minus T is going to have a small value, which means that C1 will be given a small weight. And since C2 is given a weight of T, it's going to get a higher and higher weight as we get closer to the endpoint. So this linear interpolation captures our intuition that the color of a point should be more similar to the vertex that's closer to. Now, to calculate the interpolation value T, you can follow the simple formula here. So T is given by the ratio of two differences. In the numerator, we have the difference between our point P and the starting point V1. So we are going to calculate the difference between P and V1, and then we are going to compute the distance, the norm of that vector. So this will just tell us how far P is from the starting point. And then we're going to divide that by the denominator, which is given by the norm of V2 minus V1. So we're calculating the norm of the difference between the two endpoints of the line, which means that this corresponds to the length of our line. And this denominator normalizes T to make sure that it's going to range between 0 and 1. If P is close to V1, then the numerator will be very small and it's going to be close to 0, and therefore T is going to be close to 0. As we move closer and closer to the endpoint V2, the numerator is going to become more and more similar to the denominator. And so we're going to get a T value of 1. So we can then calculate this, we can then use this linear interpolation formula to calculate the interpolation values for blending colors along the line. Any questions about this? So hopefully this linear interpolation example gives you some intuition of how to interpolate colors on a line. And we can think of barycentric interpolation as a generalization of linear interpolation to triangles. So rather than interpolating colors between two vertices, we are now interpolating colors between 3 different vertices instead. Now, similar to linear interpolation, barycentric interpolation is going to calculate the color for point P as a linear combination of the colors at the 3 vertices of our triangle. So for every color C0, C1, and C2, we're going to define the corresponding interpolation weights, U, V, and W. So these interpolation weights are similar to the interpolation variable T that we use for line. But in the case of triangle, instead of just one variable, we now have three different variables for each of the vertices of our line. So to compute the barycentric interpolation for point P, we need to somehow calculate the UVW values for blending those colors. Now, there are lots of different ways that you can use to calculate these different weights. We're going to cover one particular method, but there are other ones as well. And the idea with this method for calculating the barycentric coordinates, the interpolation weights, is that we can determine the interpolation weights by using the area of three different subtriangles. Okay, so we'll talk about what these triangles are in a little bit, but the idea is that we can take the big triangle and we can split it into three smaller triangles with areas A0, A1, and A2. The area of these three triangles are going to add up to big A, which corresponds to the area of the original triangle. And the barycentric coordinates will be given by the ratio of the small triangles with respect to the area of the large triangles. So U is going to be given by A0 divided by big A. Similar, V is going to be A1 divided by big A, and then W is A2 divided by big A. Now, by calculating the interpolation weights in this way, we have the property that if we add up the weights, UVW, this gives us 1, which should hopefully make sense. The interpolation weight should range between 0 and 1. Now, the way that we are going to construct these three smaller triangles is that we are going to take our point P, and then we are going to introduce new edges that connect point P to the three vertices of our triangle. So we're going to add three edges connecting P to V0, V1, and V2. And these edges are going to split our big triangle into three smaller triangles. And we are going to use the area of these smaller triangles to determine the barycentric interpolation for our point P. So if we apply barycentric interpolation, we might get colors like this for the different points inside our triangle. Okay, so let's step through this to see how this works. So at first, this might seem like a little bit of a strange way of calculating interpolation weights for a triangle. Like, why would the area of these small triangles even give us the correct interpolation values? To build a little bit of intuition of why this method works, let's take a look at what happens to the interpolation weights as we move the point around inside the triangle. So let's say I take my point P, and then we're going to move the point, or we're going to move point P towards the vertex V2. So the interpolation weight for every single vertex is given by the area of the triangle that's on the opposite side of P. So V2, the weight of V2 is given by the area A2. So this is the triangle that is not connected to the vertex. So the weight of a vertex is given by the triangle that's not connected to the vertex. So V2 corresponds to A2, V0 corresponds to A0, which is the triangle on the opposite side of P. And similarly, V1 is going to be given by A1. So when we move the point P closer and closer to V2, the smaller triangle A2 grows in size. And as we move the point P closer and closer to V2, at some point, A2 is going to dominate the entire triangle. So in this case, A2 is pretty much the same area as the original triangle, which means the weight on V2 is now going to be effectively 1. So this gives us the intuitive behavior where as a point gets closer and closer to a vertex, the color of that point becomes more and more similar to that vertex. And this gives us the intuitive behavior that the color of a point is determined by which vertex it's closest to. Right? So to calculate the barycentric interpolation, we just have to calculate the area of all of these smaller triangles. But I guess any questions about this example? It's a little bit strange when you first see it, but I guess if you kind of go through the examples, it does kind of give you a sensible behavior. Right? So in order to calculate the barycentric interpolation rates, we need to calculate the areas of these different triangles. Okay. Right. So now the question is, how do we calculate the area of a triangle? So I'm sure all of you have done this before in like high school trick. So you probably know a bunch of different ways of calculating the area of a triangle. But today we are going to introduce our convenient method for calculating the triangles. So for calculating the area of a triangle that doesn't require any trigonometry. So as you might know, calculating trig functions like sines and cosines on a computer can be pretty inefficient. So we're going to look at a method for calculating the area of an arbitrary triangle without requiring any of those trig functions. And the key idea for this method for calculating the area of a triangle is to take our triangle, and we're going to pick one of the edges of the triangle. You can pick any edge you want, it doesn't matter. We just pick an arbitrary edge, and then we're going to mirror the triangle along that edge. So this is just taking our triangle and then creating a copy of it and flipping it along one of the edges of that triangle. When we mirror a triangle along one of its edges, what we get is a parallelogram. So when we put these two triangles together, they give us a parallelogram. And the key observation here is that the area of our original triangle is equal to half of the area of this parallelogram that's formed by mirroring the triangle along one of its edges. Okay. Which means that if we want to calculate the area of the triangle, we just have to determine the area of a parallelogram and divide that by half. Okay, so this might seem kind of like an indirect way of calculating the area of a triangle. But the reason why we want to do this is that we can actually calculate the area of a parallelogram in a very efficient manner. To calculate the area of a parallelogram, we can take the two edges of a parallelogram. So it can be any two edges. It just has to be the two edges just has to be adjacent in the parallelogram. We can take these two edges of the parallelogram and we can calculate the the cross product between these two edges. So in this case, the vertices are in 2D. So when we calculate the vector for these two edges, so let's say we take these two edges here, we can calculate the vector for those two edges by computing the difference between V1 and V0 and computing the difference between V2 and V0. And this gives us two edges that correspond to two of the edges of the parallelogram. And we can take the dot product between these two vectors, which is going to be given by this formula here. So because we are in 2D, the cross product of two 2D vectors is given by this formula. So it's V1 minus V0 multiplied by Y2 minus Y0. Minus Y1 minus Y0 multiplied by V2 minus X2 minus X0. Right, so you just plug into this cross product formula, and it's going to give you some value back. Now, the thing to be careful of is that the cross product can be negative. So depending on the ordering of the edges that you use to calculate the cross product, you might get positive value or you might get negative value. But since we know that the area of a parallelogram can't be negative, we take the absolute value just to make sure that we only return the positive area. Okay, so once we have the area of the parallelogram, we just divide it by half, and that gives us the area of the triangle. And we didn't have to use any cosines or sines. Okay, so with this method, the way that we calculate the interpolated color at a point P in a triangle is that we just apply this parallelogram method to calculate the area for each one of these small triangles. We divide the area of the small triangles by the big triangles to get the interpolation weights, and then we use that to blend the colors of all three vertices. Okay, so I think we'll wrap things up here, and then we'll continue through the lecture on Friday. But any final questions before we end for today? Okay, if not, then I'll see you on Friday.